All right, so yesterday we were just trying to work with identifying if a graph was linear, quadratic, or exponential, right? So today we're going to do more with that. But once we identify if it's linear, quadratic, or exponential, we're going to be able to write a function for that model. So just right up here we have the standard forms for each kind of model. So linear, y equals mx plus b. What does m stand for? No linear function. Slope, right? And what is slope again?
Rise over run.
Rise over run. So our change in y's over our change in x's, right? Y equals ax squared plus bx plus c. That's a quadratic model. So if a is greater than 0, what would your function look like? Would it open up or would it open down? Open up, and if it's negative, it'd open down, right? Then we go on to exponential. Y equals a b to the x. What's our a?
The first number in the sequence.
Our starting value, right? And what's our b? What is our b value for an exponential function? No.
The ratio.
Constant ratio, right? So that's what we're multiplying our terms by to get the next one, right? So, why did that happen? Okay. So, we're just going to move on to this little example. Use the data in the table to describe how the software's cost is changing, and write a function to model the data. So before we even do anything, what's happening to the cost as the years go on? Going down, right? So we can say that right away. So, to decide if it's linear, quadratic, or exponential, we do what first? If it's linear, what do we do? If we're trying to check if it's linear.
Look for a common first factor.
Say that again?
Looking for a common first factor.
No.
That was
Second difference?
Not second difference,
If there's
first difference. So, linear models, if there's a constant first difference, then that'll represent a linear. If there's a constant second difference, that'll represent a quadratic. So here they do our first differences, 80 minus 72, or 80 to 72, they're just subtracting 8. 72 to 64, or 64, 80, is minus 720. So right away, is there a constant difference? Nope, not a constant first difference. So then we can say it's not what? It's not linear, right? So then we can say it's not linear. We move on to check if it's quadratic. And we do that by checking the second differences. So we have plus 0.8 and then plus 0.72. Are those the same? Nope, so there's not a constant second difference. So it's not what?
quadratic.
It's not quadratic, right? So, next thing we do, we said it's not linear, it's not quadratic, so what's the last thing it could be?
Exponential.
Exponential. And how do we check that?
If it's multiplying by the same number over and over.
And what's that called?
Constant.
Constant ratio. So if there's a constant ratio between each of our y values, we can say that it is a
exponential.
exponential function. So how are they getting that 0.9, that times 0.9?
Because it's a chart.
Marky?
If you multiply it, like 58.32
Mhm.
times 0.9, that's going to give you 64.
Is it?
The opposite.
So how do we find that 0.9 first?
Divide.
Malcolm?
Divide.
Divide what?
60 by 72.
So you did 64.80 over 72.0. And did you get 0.9? Yeah, so that's how we find our constant ratio. So there's a constant ratio, we can say that this is a
Exponential.
exponential, right? So, once we found out that what model it represents, this one's an exponential, now we get to write the equation for it. So just right away, they write the standard form for an exponential, y equals a times b to the x. Then they just substitute in the values we know. So what does b represent again?
Ratio.
Constant ratio, and what is it?
0.9.
0.9, so they just substitute that in there. Then they have substitute those values in. So they put 80 in for y and 0 in for x. Why would they do that? Where's that 80 and 0 coming from?
On the top, like the 80 is the y and the x is a 0.
Yep, we have a y value of 80 and an x value of 0 in our table. So they just plug those right into our function that we have there. So what's 0.9 to the 0 power? 1, because anything to the 0 power is 1, right? So a times 1 is a. So a equals 80. So far we got our a or b value right away. Then we found or solved for a. So once we have our two variables a and b, we can rewrite our function.
I have to ask a question. Did they really need to go through all that work of finding a? What does a represent, you guys, again? What is a? In an exponential function, a is representing the what?
First constant.
Not the first necessarily, but kind of.
The y.
Not the y. Come on, what is a representing in an exponential function? It's something to do with some amount. Which amount?
Starting.
The starting amount, it's what it starts at. So when x is equal to 0, what is the y value? Or in other words, what's that starting amount? Did the table already give that?
Yeah.
What did the table say? When x equals 0, y equals 80. Isn't that how we always found our a when we were writing exponential functions?
Yes.
We would look in the table, we would find where x was equal to 0, we would find our y value and say there's our a value. So in reality, they did some extra work here that they really didn't need to do because we already knew what the starting amount was, but it did verify that the starting amount is 80. Okay, so I don't want that to confuse them. Okay, so in reality, once we can identify A and we can identify B, we are really ready to set up our model. We're ready to set up our function, okay?
All right, so we'll just move on to that first problem there. First thing it says, describe the model that best fits the data below. So how would we go about figuring out which model best represents that?
Well, that one is exponential.
Okay, why?
Because it's just like this one, right? The second one at the top.
Multiply everything times
Okay, so you say there's a constant ratio, so how would we find that?
Multiplying. Or seeing what's being multiplied.
You could divide one multiply.
Okay, so if we divide what by what, we can find what?
4 and 1.
4 divided by 1 equals
4.
4, 16 divided by 4 is,
4.
and then 64 divided by 16 is
4.
4. So we have a constant ratio of 4, right? So we can say our b value is 4. Then I'll just rewrite the... So if there's a constant ratio, we can say that this is what kind of model?
Exponential.
Exponential, so right over there, exponential. Now, what's our a value?
Starting on is
1, because when x is 0, y is 1. So, now that we have our two variables, a and b, we can rewrite our function, so it would read as what?
Y equals 1.
parentheses 4x.
Okay, do we need that one in front there?
Wouldn't X be zero? Wouldn't X be zero?
X would be 0 if we were looking for the starting amount, Malcolm, okay? But we're not looking for the starting amount, we got it from the table. Okay, so we only replace A and B in our function.
All right, so.
So yes, we do need the 1 to start with, Mr. Conlon.
So we have our function rewritten. Can we clean it up in any way? Okay, how?
Can we put something in for X?
Nope, we're just trying to rewrite our function right now. So there will still be an x in there, right? Or
2x power.
to the x, right?
So why can't we take that 1 out of there?
1 times 4 is 4.
Well, we don't do multiplying first, we do powers first.
Because
Doesn't change it, 4 to the x power would get multiplied by 1, would it still be 4 to the x power?
Yeah.
Yes, it would.
All right, moving on to number 2. We have to decide what kind of model best fits this set of data, so
linear.
linear, why?
Because you're adding 3 basically.
So we look for our common first difference, right? So we go through that. 7 to 10, we are doing what?
Adding 3.
Plus 3, 10 to 13, adding 3.
So,
Yes.
since we're adding, how come we associate it with a common difference? And difference is associated with subtraction.
Okay, so was adding 3 is the same as subtracting what? A what? Adding 3 is the same as subtracting, no, adding 3 isn't the same as subtracting 3. Giving you $3 and taking $3 from you is not the same thing.
0.
Subtracting, adding 3 is the same as subtracting negative 3. So in reality, it's still like we can talk about it as a difference. It would be subtracting a negative 3.
That came up.
This is, yeah,
Literally
this has been cleaned up, yep. Now, there's one thing we are forgetting to do though, both times. What has to be true in the x's?
They have to have one constant.
They have to have a common difference also, the first time. So we always have to check for that. Don't take it for granted. So are the x's going up by the same amount or going down by the same amount every time? You need to check that out.
Yes.
Okay, so for number 2, there's a common first difference, right? So what kind of model is it?
Linear.
Linear. So then we have the standard form for it. So we have to find 2 variables. We have to find our m and we have to find our b. So how would we go about finding our m?
0, 7.
Well, m is our slope, right? And slope is,
Ratio.
hmm?
One is square, one is
Rose, what's our slope represent? Rise over run, right? So, rise over run, our change in y over our change in x.
That's what m equals m.
Mm-hmm. So what is our change in y, or what is our rise?
3.
3. And then what's our change in x, or our run?
1.
1, so our slope is
3.
3. There we go. So we found our m, now we have to find our b. What's our b in a linear function? say that?
Yeah.
Okay. So B represents the y-intercept in linear functions, right? Yes, no, maybe.
Yeah.
Yes, so when we plug, or when x is 0, what is y? 7. Right there. So we have our m and our b, right? So we can rewrite our function. So y equals what?
Parentheses 3.
X. Listen.
How come we don't put parentheses around x of the 3? Because we're so multiple.
We could do that. So we're taking 3 times x. If we do have parentheses, let me clean it up. Yep, so what would that be rewritten as? Is what we had before, right? Because the 2 parts of our problem were describe the model. We did that. Then after we do that, we have to write a function for it. And we did that right there.
Just out of pure curiosity, raise your hand if you really remember working with y equals mx plus b last year. Sweet, so where would b be on a graph?
Where the y touches the axis of the.
Speak up and sit up, I can't hear you. I'm getting old.
Um,
Where would b be on our graph then?
This is the x, and then wherever it touches.
So it'd be right on
Yeah, those are
Y-axis.
zero,
the
seven.
y-axis, right? So if you don't have that stuff down in your notes, write it in your notes because it's no place else on those notes. And if I'm walking around and I see you don't have that stuff, I'm not gonna help you out. So if you have not taken the time to write the rise and run and the B, write it down, please. And I will share that information with Ms. Sagermont too. Okay? Sorry.
No, you're fine. All right, does anyone have any questions about what we just went through? Any questions of what should be on the homework? All right.
So does anybody need that left up to write down, or does everybody have it written down?
All right.
We recorded this.